Hi, my name is Ondrej Čierny and I'm a grad student in the MIT Star Lab. And today I'll be talking about testing of the CubeSat Laser Infrared CrosslinK or ClickA payload, which is a payload that we're jointly developing with the University of Florida and the NASA Ames Research Center. And the purpose of the CLICK project is to demonstrate the feasibility of optical crosslinks and downlinks with nanosatellites using miniaturized optical transceivers. And CLICK is actually a two-phase mission. In the first phase next year, we'll fly the ClickA payload, which is a single payload that will fly on a 3U Blue Canyon Technologies bus, and it is a risk reduction mission that will verify some of the key technologies needed in these optical transceivers, specifically including a MEMS fine steering stage, the transmitter optoelectronics, and some of the optical ground station hardware. Now with ClickA, we're targeting a higher than 10 megabits per second optical downlink from an ISS orbit onto our 30-centimeter portable ground telescope. Then in the second phase, in 2022, we'll fly the Click B and C spacecraft, which are again payloads for a 3U bus. And these will demonstrate not only optical downlinks, but also full duplex crosslinks with precision ranging between the two spacecraft. And with Click B and C, we're targeting a higher than 20 megabit per second optical crosslink at a range of up to 580 kilometers, with precision ranging of half a meter or better without GPS between the two spacecrafts. And we believe that these features in particular will be especially useful for future coordinated observation missions, for example, based on swarms of nanosatellites. So in this presentation, I'm going to focus on the ClickA payload and talk about some of the recent testing that we have performed to prepare it for its early 2021 launch. My colleague Peter Grenfell has another presentation where he's talking about the Click B and C spacecraft. So be sure to check that out. He's going to give a lot more details on the design of these two future payloads. So the way that we facilitate the optical downlinks with ClickA is that we use a kind of two-stage approach to alignment between the spacecraft and the optical ground station. We have an initial open-loop course alignment phase, which is based on the spacecraft body pointing and the ground station tracking through its gimbals. After that, we have a secondary closed-loop fine alignment phase, where we uplink a beacon laser at the spacecraft, which it acquires on a beacon camera and uses a MEMS fine steering mirror to lock onto it. After this, we activate the downlink laser, which then the ground station acquires on its tracking camera and uses another fine steering mirror to help stabilize the beam on its detector, and thus completing the secondary fine alignment between the two. Now, if you look at the payload design itself, we can see that ClickA is split into kind of two halves. The top half is the optical bench, which hosts most of the optics for the fine pointing system, and the bottom half hosts the transmitter optoelectronics, which include, for example, a fiber amplifier and the modulation electronics. If you look at the payload from the top, we can see the beacon, camera, and lens assembly, which are used to focus and track the beacon from the ground station. We can see the transmit collimator, which is used to create a collimated downlink beam at our wavelength that goes out of the system. And we have the MEMS fast steering mirror, which, again, as I mentioned, is used to do the actual fine steering of that downlink beam. Now, one of the remaining high-risk items, which was not previously tested in terms of performance in a space environment, is the beacon camera and lens, which are actually both commercial off-the-shelf components. So we're using a COTS silicon focal plane array, and we're also using a COTS 6-element lens assembly from Schneider Optics to focus the beacon onto that focal plane array. And in particular with this lens, we don't know its inner structure or even the materials used inside of it, which raise several concerns. Firstly, because of outgassing. Secondly, because of potentially trapped air in between the individual lens elements, which could contribute to stress of the optics or even damage the lens itself if not vented. And thirdly, we're also concerned with the stability of the focus of this lens as a function of temperature in vacuum. So to address all of these concerns, we have performed two tests. Firstly, we have performed a passive week-long kind of survival/outgassing test, where we put the entire lens assembly into vacuum chamber for a week. And to measure any degradation, we have performed optical transmittance tests through the lens before and after this week-long exposure. And fortunately, not only did the lens survive perfectly, we were also not able to measure any difference in transmittance before and after this test. In a future test, we also want to measure the actual outgassing rate from this lens to assure that it won't contaminate any other optics in the system. And finally, to address the last concern, the focus stability, we run actually a full active thermal vacuum test where we perform periodical centrating of the point spread function from the beacon laser on the detector itself. And we perform the minus 40C to 40C cycle for this. And to be able to run this test, we are very lucky to have been able to use a phenomenal facility that was developed at the MIT Kavli Institute to help with testing of the test spacecraft cameras, one of which you can see here. So in this lab, we have the thermal vacuum chamber with a large optical viewport on top, above which we have a beacon source, which is essentially a large off-axis parabolic collimator that is used to imitate plane waves coming into our payload at the beacon wavelength. So inside the chamber, we have the engineering model of our payload, which includes the camera and the lens assembly here, and several RTDs which we're using to monitor the temperatures. And to actually cycle the payload, we're using a heater that sits below the camera plate, which we use to raise the temperature of the lens assembly, the blue color here, to about 50°C, after which we slowly cool it down through radiation with liquid nitrogen that's pumped into the shroud in the chamber. And you can see the results of this test summarized in this slide. So what we did, as I mentioned, we were sampling the point spread function of that beacon laser on our detector as a function of temperature periodically. So you can see that on these images here on the left. And to be able to assess the change, we fit Gaussian distribution to these images for each image, which essentially helped us to calculate the diameter of that spot as it was changing over temperature. And both from these images and from that Gaussian fit, which you can see on this graph here, we can clearly see that there is some spreading in the point spread function happening, or defocus, with increasing temperature. Now, fortunately, this effect is not too large. It's only a few pixels, and it's well within our margins and our beacon uplink budget. And we were also able to perform centroiding successfully over the entire temperature range without having to change any centroiding parameters, for example, the camera exposure time. So the spreading was definitely not too severe. We can also see there's some slight astigmatism or difference in the XY spot diameter in the system. However, we believe that this is not due to the lens itself, but it might be due to the source or the off-axis parabolic collimator that we're using to create the collimated source. And OAPs are kind of difficult to align very precisely, so we believe that this astigmatism might be due to some slight misalignment in that OAP. Now, in the range that we're interested in, which is about from 0 to 25 degrees, which is our operating range, we're well within our allocation of a 1 dB impact on the beacon uplink signal to noise ratio, which is pictured here as the red line. So moving on, one interesting concern that was revealed while doing this testing with the beacon receiver had to do with optical deformation. So what we're using at the payload for stray light isolation is that we have a bandpass filter which sits at the aperture of the payload. And when we place the bandpass filter into our payload while doing the beacon receiver testing, we noticed that it contributes to spreading of the point spread function, which led us to believe that it's maybe not perfectly flat and it might be slightly curved. And to verify this, we actually measured the surface of that filter using a Zygo interferometer. And you can see the result of the measurement here. It showed that there's clearly some curvature, which is of several wavelengths, in fact. And if we decompose the measurement into surface aberrations, we can see it adds a lot of defocus into the system, which agrees with the measurements we have performed with the beacon receiver that showed the spreading of the point spread function. Now, fortunately, we can compensate for this effect by refocusing that lens assembly. And we believe that this effect occurs because of the coatings on the filter itself. The filter is of a special dual bandpass configuration, and it has a lot of dielectric coatings on the front side of the filter substrate, which might contribute to its warping. Now, interestingly, a similar deformation effect occurs on the fast steering mirror here, albeit for a very different reason. So the fine steering mirror is a small silicon substrate which is coated in aluminum. And aluminum is about 5% absorptive at the wavelength of our transmitter. So about 5% of our transmit power is absorbed by the mirror and contributes to thermal deformation of the mirror itself, which again leads to deformation. And we were also able to obtain a zygo interferometer measurement of the deformation with the help of our colleagues in the Facebook Connectivity Lab. And you can see the result of that measurement here. And looking at the decomposition again, we can see that the primary effect is again in defocus. However, this time it's a lot less severe than the defocus due to the bandpass filter itself. So for the ClickA payload, this is not a very severe impact and we can neglect it. However, we have been able to confirm that this effect gets much worse with increasing transmit power. So for future payloads, which will use potentially much higher power lasers, this is definitely going to be a concern. Now, I mentioned that fortunately we were able to compensate for this defocus effect by refocusing our lens assembly. However, we are not able to compensate for it in terms of our transmit beam. Our transmit beam will also experience this defocus, which might contribute to spreading of the transmit beam. And since we're using a fixed collimator here, which we're not able to refocus, we cannot really compensate this effect. And to verify that this effect won't be too drastic for our transmit beam and will not contribute to spreading of that beam, we essentially wanted to verify the divergence of the beam coming out of the system. And to do this, we performed beam profiling of the transmit beam coming out of the payload using a scanning slit infrared beam profiler, which allows us to measure the beam radius or beam waist at different points in distance from the payload. And to be able to cross-check those measurements, we also calculated the predicted evolution of the downlink laser in space as a function of distance based on the specification of the fiber and the collimator itself. And you can see that here as the blue curve in this graph with some uncertainty, which is due to the manufacturing specification of the fiber and collimator itself. And based on the red dots here, the measurements you can see, we're definitely still within the specification of the fiber and the collimator, which is good news, and it means that the defocus added due to the bandpass filter and the mirror is not very severe and does not really contribute to spreading of our transmit beam. However, for our future ClickBNC payload, which will use much narrower divergence, we expect that this effect might be much worse and might contribute to spreading of our transmit beam. So one of the lessons learned from all of this testing was to try and use both side coated bandpass filters with at least anti-reflection coating on the back side of the filter substrate, and to avoid essentially this way the stress-induced curvature on the front of the mirror of the filter. So moving on, I'm gonna switch from talking about some of the testing to talk about some of the lessons we have learned by trying to manufacture and actually integrate our payload. And one of the biggest lessons we have learned had to do with fiber management in our payload. So Click actually has a lot of fiber components, and keeping all of that fiber organized and maintaining a proper bend radius is critical in terms of maintaining a high output power from the payload. And to assist with all of this organization, we developed this fiber raceway, which was probably one of the biggest challenges in terms of optomechanical design in the payload. And this fiber raceway has gone through several iterations to help with the manufacturability in our payload. Specifically, we had problems with the tolerances on the fiber paths in this raceway, which led us to switch recently from this kind of precise arrangement of each component and each fiber to a kind of more open fiber raceway where we only have holders for the specific fiber components and use only a few points to help with routing the fibers, which might be varying in length, to help with maintaining the bend radius. So this has been a great learning experience in terms of the manufacturability of the payload itself, and for ClickBNC it helped us do a lot of simplification and redesigns in making the payload much more manufacturable. Now finally, we had a lot of developments in the optical ground station too. We have finally finished the design of the telescope backend, which sits behind the telescope and it essentially holds the receiver. Now previously we had a very hacky setup where we had a huge optical bench that was mounted behind the telescope. Now we have actually a very lightweight structure and also an optical shroud, which not only helps protecting the receiver from the elements, but also helps with stray light isolation of the receiver. We've also procured the high-power beacon laser and collimator, which will sit on top of the telescope and will be aimed at the spacecraft. And we also found a new home for the actual deployment of our ground station at the MIT Wallace Observatory. Now, obviously, we don't want to test these new high-power lasers in the middle of Boston, which is very densely populated and also has an airport. So to summarize, ClickA is in the final phase of development. We have done a lot of optical testing to verify the beacon receiver performance and also the transmit beam divergence. We've redesigned the fiber raceway such that it is much more manufacturable, and it's currently being assembled. We also tested the final flight electronics, which were recently assembled, and we'll proceed with environmental and functional testing of the fully integrated payload soon this summer. And finally, in the fall of this year, we expect to integrate with our spacecraft bus at Blue Canyon Technologies, and we're hoping for early 2021 launch on the SpaceX commercial resupply 2022. Thank you for your attention.